Okay, so good morning, everyone. Welcome to the last lecture of Professor Morten Hjorth-Jensen. You all know what it is about, so I won't waste too many words. So, Morten, if if you are ready, you're welcome to start. I just wanted to, sorry, I just remembered to mention to the participants that tomorrow, after the last lecture, tomorrow afternoon, I think the last speaker will be Ilya, if I remember correctly. We have a 20 minutes, half an hour closing ceremony to which we have also invited some stakeholders from the Department of Science and Innovation who will say a few words. And also the director of the CHPC. So it would be really nice if all of you would make an effort to join us there. And also that could be an opportunity to take a famous Zoom screenshot of all participants just for a kind of memory of the school. So please, and I will ask Benjamin. I don't know if he's here now. Okay, no, I don't see him now, but I will ask him to send a reminder everybody again with the link for the closing ceremony. Okay, Morten, sorry, this was my service announcements. Now you're welcome to start with some interesting science.
Thanks so much.
Thank
And
you.
thanks to everybody for coming again. The chat is open, so feel free to ask questions if you want to. Just put them in the chat. Or if you want to unmute yourself, you can do that as well. Now, the last topic is about neural networks and normally what we call deep learning. So I wanted to give you, after we've gone through logistic regression and linear regression, and we set the scene with entities like this logistic function, which is now used as a probability for classifying specific events like a yes, no, plus, minus 1, 0, 1. So these were the so-called binary cases. This can also be extended for classification problems to many more classes. And one of the examples we're going to look at now when we're going to build a code for the neural networks is this database over handwritten numbers. So that means that you have 10 classes. Now, there are many types of neural networks. So just to get through the woods, to see the wood for the trees, let's just take a quick look at some of the basic things which we are going to encounter. In my notes, there's this link to Aurélien Giron's book, which is pretty good and has a good discussion of many of these things in chapters 10 to 11. That's for the basics. And then there's also a series of other chapters with more advanced methods. I plugged in a video on neural networks, which I think is pretty good. And then, in addition to you having to calculate gradients, there is a famous algorithm, which is the way we update the parameters of a neural network. So in a neural network, what we end up with are weights of different nodes or neurons. And then we have to, in addition to the weights, we would have something which are called biases. And these are the parameters. And we can have zillions of these parameters. It's not like the simple logistic regression case we had or the linear regression case, where we typically end up in the tens or perhaps 20, 30 parameters. Now we can easily, when we are training a neural network, we can easily have hundreds of thousands of parameters. So that means that this optimization problem becomes a very delicate one. So to have an efficient way to find the optimal of a function we want to minimize is a central issue in essentially all the learning methods. So on Tuesday, we scratched the surface of these gradient descent methods. These methods play a central role in basically any deep learning algorithm. So these are what they are. They are computational systems that can learn to perform tasks by considering examples. So you need to have data which are labeled. And that's often an expensive part of the job. So neural networks and many of these deep learning methods like convolutional neural networks, recurrent neural networks, the very popular methods, they rely on lots of data, and that the data are labeled, and they are very data intensive methods. The more data you have, the better they perform. And what we normally do then is that we split the system into different layers. So what I'm going to do now, before we actually move on with some of these standard definitions, is actually to write down a neural network and with the basic ingredients. So let's switch quickly over to the whiteboard and draw the first neural network and bring in some of the basic concepts. So when you look at the basic setup of a neural network, and this is also the setup of a recurrent neural network and also a convolutional neural network, so more complex ones. So what we would have is an input layer. This is our standard input. So input. So if you have an image, and suppose this image contains now 64 pixels. So it's a two-dimensional object entity, and it has 8 pixels in one direction and 8 in the other one. So you would have 64 pixels. These would be your inputs. So the input would then be given by different nodes or neurons, as we call them. So these are normally labeled with an A. So this would be an X1. I would have an X2 here, and so on, till the final input Xn. So we are feeding into the system a set of inputs. And these can be set up in the same way as we did with logistic regression and linear regression. So we would typically here have the design matrix. X. Now if we want to classify a series of images and each have 64 pixels, then you would have 64 times the number of images which you would feed into the neural network. So for each image, you would now train the network to reproduce that specific image. So if this is a number 2, you want the network to train a network so that you actually reproduce number 2. So what you have next now is a set of hidden layers. And we are going to call this could be hidden layer 1, hidden 1. And we just write it with an H of 1 here. So, and here we would have different nodes as well. And they don't need to be the same as you have in the input layer. So this is a hidden layer. And it's called hidden because we never print out the output from a hidden layer. So it's something which you never actually look at unless you want to print it out. What you're looking at is the input and the output. So the input now, since this is going to be a so-called supervised learning case, the input is always fixed. This is your input. You don't change that one. If you're dealing with unsupervised methods like Boltzmann machines, then the input can be changed continuously. But we are going to stay with supervised learning. So these feed into the hidden layer. So here we would have a hidden node, or a neuron has been called, or just a unit. So I'm going to switch between neurons, nodes, and units. And so this would be unit 1 or node 1 of layer 1. And then we would have number 2 of layer 1. And this goes all the way down to an H of M. So M and N don't need to be the same. So that gives you another set of parameters in the theory. The number of nodes in the hidden layers and the number of hidden layers, they become parameters in your theory. So on Tuesday we discussed the new parameter, which was this learning rate in the gradient descent method. And then we had this shrinkage method like ridge and lasso, which introduce another parameter. So now if we start counting the parameters, we could have this hyperparameter lambda, we have the learning rate, we have the number of hidden layers and the number of nodes in the hidden layers. They can also change from layer to layer. And in here, we normally have a bias. So this another quantity here, which I'm just going to bring in like this. So this feeds in, and this is a b of 1. Now you can treat that as a vector. So this is normally plugged in order to avoid that your network has a 0 output. So it will always have an output which is different from 0. So this b is called a bias, and it's normally set to a small, eventually random value. And this is to guarantee also that the training of the network doesn't stop up. So what we will have now are connections between the input nodes and the nodes in the hidden layer. So each node is now connected with the hidden nodes. You can, when you come to convolutional neural networks, you can set up less connections. So this is normally a so-called affine operation, where we now develop a matrix which connects the inputs to the hidden layers, and this matrix is normally called the weight matrix. So you can now think that there's a weight here, 1, 1, which goes to layer 1, the hidden layer 1. So we have a connection from the input node 1 to the hidden layer node 1. And then we can repeat this one with all the other nodes in the input layer. So this will be 1, 2, or 1, and it goes all the way down to 1m for 1. And then we can repeat this one for all the other ones. So you can think of this one going in here, that one sending in a signal in here, etc., etc. So you see the basic pattern here. So that gives us a matrix, W, which now contains the information about how these nodes are connected. Now your nodes here, they produce an output, which then goes into the next hidden layer. So we would have a layer 2 here, which would be an H2, and then we would have the different nodes in here, and all the way down here. And they don't need to be the same number as the one in the previous hidden layer. And this can continue now. You can have many such hidden layers, and the more you have, the deeper your network becomes, and this is why this is called deep learning. And then it continues till the end, till the output layer. So if I have only a plus minus case or yes and no case, there would just be one output. If I, on the other hand, want to classify the 10 numbers from 0 to 9, then I would have 10 possible outputs. So now I'm just drawing this as an output, and I'm going to call this output for y tilde, or I'm just going to call it for y. And then this is going to be compared with the targets. So we have some targets, which are the final values. Compare with targets. And I label the targets with a vector t. And when we have that, then we can set up our cost function. And this is the function we want to minimize. So we are sending signals through the whole network. So this proceeds all the way here. And there will be a weight matrix here, which now connects layer 1 with layer 2. There will be a new weight matrix here. And this continues all the way, and you will have biases here. So there will be a bias for the second layer. There will be a bias for layer L. And finally, we have the final layer, which we can label with an uppercase L. So that produces an output. Now, these outputs are generated by a function. And a typical function, so you feed in something to the given node, and that node sends an output. That output is then produced by a function like the logistic function we discussed, or some other type of functions. So that gives us another parameter. And then when we reach the final layer and produce the output, we want to compare this output with the targets. And then we when we compare the targets with the outputs from the network, we minimize the cost function. And then we use something which is called the back propagation algorithm. And then we update the weights. So we proceed back again till we reach the first hidden layer. So remember now that the inputs are never changed. The targets are the same. These are the values we want to reproduce. But the output we produce now is based on this back and forth moving. So you move back to the first hidden layer with a back propagation algorithm, which involves a gradient descent algorithm. So you would now optimize the gradients of this cost function in every hidden layer, starting from the output layer. So this quantity here is the output layer. That's the final one. So what we end up now is a new set of parameters. So if you want to collect all the parameters we have, so we are going to do a forward move through the network, and that produces an output. And we call this output y tilde. Then what we have is a back propagation from output layer to the first hidden layer to, and I write this as a first hidden layer, and this updates. This is the way we update the weights and biases, which are now the parameters. And you see very quickly that if you have lots of nodes in a hidden layer, you're going to get many parameters. We are going to see some explicit examples now when we are going to train this data set of handwritten numbers. So you would update the weights and the biases with a gradient descent method. So that's the working horse of any kind of neural network algorithm or any machine learning algorithm with gradient descent. So you produce an input, you have an input, you feed forward this information to the final output layer. This produces a number y, or set of numbers. You compare that with the targets, and then you need to set up a cost function, which gives you a measure of whether your model is doing well or not. Then you back propagate the information till the first hidden layers, and then you go back and forth till the difference between the targets and the output from your model differ by a negligible quantity, or that you have some prefixed way of stopping the training. So this brings in parameters. So in the gradient descent, we would have the learning rate. So the parameters which we can fine tune now is one, the learning rate. So that becomes a parameter. We would also have the number of nodes in a hidden layer. Number of nodes. We would also have the number of hidden layers. Then what we also can have is these hyperparameters lambda, which we discussed in connection with the linear regression and also logistic regression. So we can fine-tune these hyperparameters lambda, which normally reduce the mean squared error if we are doing a fitting a function problem, or they can also show to reduce the variance of the problem. So this hyperparameter is often tuned to reduce the bias and the variance of your model. Then what we also can do now is to look at so-called activation functions. That becomes also a set of parameters which you would have to play around with, activation functions. So what happens then is that a given node, let's call this a node in layer L, and this node has a label I, so that receives input from all the previous layers, so the nodes in the previous layers, they produce an input here. So there will be a weight here, wij, there will be an wil, a wik, and so on. And this node here produces an output, which is then fed into the next layer. So in order to produce this output, there is a function. So the input which you see here is something which we are going to call z. So there is an input to this specific node, z of I, which is now going to contain the sum over all the, so there's going to be an I of j, and this is going to contain the output from the previous layer. So this goes into, these are the weights which connect the previous layer with the present layer, and these AJs are the outputs from a node j in the previous layer, L, so this is going to be an L minus 1. And then there's going to be a bias, which can be the same for all the nodes in a layer, or it can be different. This is now fed into, so this is the final input to this function, and this now produces an output, AI of L, which is now given by a function f of z of I of L. This function which you see here is a so-called activation function. And a standard activation function is this logit function, or the sigmoid function, which we discussed on Tuesday. So this is so-called activation function. So if we go back to what we have here, if you now look at the network itself, so every single node here receives an input from the preceding ones, and then it produces an output, and that output is sent to all the nodes in the next layer. Now, the standard neural network, that means that it becomes from a computational point of view, it becomes pretty involved, because the matrices can be dense, and you're dealing simply with matrix vector multiplications, and you deal with a full matrix. A convolutional neural network tries normally to reduce the size of this matrix. So you are trying, by the process of convolution, you're trying to reduce the dimensionality of the problem. So the full problem, as you see here, can become pretty large. And if you have, let's say, 1 million of features which you want to fit, this dimensionality here can just become monstrous, and you want to reduce it. So standard feed-forward neural networks are normally heavy to train, and they are greedy computational networks, because you're dealing with a full matrix vector multiplications here. So the basic mathematical operation you end up doing is the operation which you see in here. This is the one which consumes time, and this is the one which is also used in calculating the derivatives of the so-called cost function. So when you come to the end point, then you're comparing your output with the targets you want to reproduce. And clearly the structure, the architecture of your network depends now on all these parameters. So there will be an activation function, and you can treat that as a variable, because there are many types of activation functions. And then you have hyperparameters lambda, you have the number of nodes, the number of hidden layers, you have the learning rate, which needs to be tuned in order to have the proper gradients. And then when you also look at the gradient descent method, there are many ways of doing the gradient descent. So you have many different ways of doing gradient descent. And if you're doing a stochastic gradient descent, where you're calculating an expectation value for the gradient using less data, then you typically end up with having additional parameters, like the number of times you want to sample over your data set, how much data you want to pick, and how you want to fine-tune the learning rate. So there are many ways of doing gradient descent. So these all become parameters in your theory. So this was a kind of bird's view on a neural network. Guys, feel free to ask questions, because else I just keep going on till we have a small break. If you don't have any questions, what I'm going to do now is just to move back to the slides, and I will stay now with my Jupyter notebook and the slides for the rest of most of the rest of the lecture. So let's just go back to the slides. So as we say here, all layers can contain an arbitrary number of neurons or nodes, and each connection is represented by a weight variable. So these are all parameters which we end up having to tune. Then I just wanted to say quickly about different types. So the standard one which we are going to look at is a so-called feed-forward neural network. And the set of parameters, as we have discussed, involves now the number of hidden layers, the number of nodes, the number of connections you want to have between the nodes in the previous and the new layer. And the models are very much inspired from biology. And the whole field of neurons was actually, meant to mimic biological systems, where you have neurons interact with each other by sending signals. And they're sending signals in form of these mathematical functions between layers. These mathematical functions are the functions which I call the activation functions. So the feed-forward one is the most common one. It's also called the multi-perceptron model. So as you saw in my slides on the whiteboard, the nodes are represented by circles, and then you have arrows which display connection between nodes, and including the direction of information flow. And this is normally called a fully connected neural network. So all nodes in the previous layer are connected with the nodes in the subsequent layer. So that's a feed-forward neural network, and that's the one we are going to go through most of the time today. And then we have convolutional neural networks, which are extremely successful in imaging. So this has been the standard method for image recognition. And in this case, we are using the mathematical process of convolution to reduce the dimensionality. So this is a kind of recurring theme, the dimensionality of the problem. So when we deal with the feed-forward neural network, we are looking at an affine transformation. That means that we take a matrix and multiply that with a vector, or multiply a vector with a vector, or a matrix with a matrix, and we keep the full information. And that clearly becomes computationally heavy when we have many features and many data. And that limits often the applicability of these, feed-forward neural network methods, since they depend on the full dimensionality of the problem. So unless you can reduce these dimensionalities, feed-forward neural networks are very data greedy, and they are very greedy when it comes to computational cycles. The recurrent neural networks are widely used in, for instance, language and speech recognition. And these are networks which now are also widely used for time series studies. And it contains information, so you can actually think of you having a network where at each time step you feed in some information to your network. So this could be something like a measurement where you measure a specific, let's say, response to something at a given time, and then you measure it at a new time, and then at a new time, and this will be connected through the different time steps. And that's called recurrent neural network. And it's widely used in time series studies, in financial studies where you have time series over stock markets, but also in language recognition. Now I'm going to skip many of these things, and I wanted to now dive more into the Jupyter notebook, because we need to look at some technicalities first. So I'm going in, these are the same slides, but it's in form of a Jupyter notebook. And one of the things we need to deal with first is actually this so-called backpropagation algorithm. So if we look at the many parameters which we have in a typical neural network now, when we look at the mathematical process, so we have a model here. If we have only one neuron, we have an activation function, and that takes in a weight. It multiplies it with the input variable. So now we're looking at a model where we simply have just one input, one set of inputs, and that feeds into only one neuron. So this function here, the activation function, is a central model parameter in the theory. So let me just bring this up here, the chat here. There's a question. Yeah, so this is a very good question in the chat here about the efficiency of the activation function. So one reason why we pick an activation function like the logistic function or the sigmoid function is that this is a function which has an analytical derivative and it's easy to calculate. So when you're choosing an activation function, it has to have some properties like those we discussed with logistic regression, the logistic function or the tanh function. And we want to have continuous derivatives because we are going to take the derivative of the cost function. And in the derivative of the cost function, you will find the activation function. So you would like to have activation functions which have analytical derivatives and are easy to evaluate, and at the same time have the right features. So that becomes very important. So the mathematical model which you end up with then is that you compute this input z. So this is the sum of what comes in from the previous layer, and then you produce an output, and this output is sent to the next layer. So when you now think of this as a matrix, so you would have many inputs. Now you have a specific node I in layer 1, and that gets an input from the input layer, and this is modulated with the weights, which are unknown parameters you want to optimize. And then there is a bias, which is normally put in there to hinder that the weights, if they by accident are 0, then there would be no output. And now you see that the output from node number I in layer 1 is now given by this activation function here with this input. And then this would continue, so you would have a general layer L, which now has an output given by this input here, which now can depend on what came in from the previous layers. So the mathematical model, if you now go into layer 2 here, you can think of this as a repeated set of matrix vector multiplications. So this would be the input from the first layer, first hidden layer, and then you have the output from the second hidden layer, and so on. So if you go to layer 3, this would now contain the input from the first layer, and then the second layer, and then you get the third node, the node in the third layer. And this would just go on and on. So basically what you have is a chain of matrix vector operations. And you see then that computing this activation function becomes a very important topic. So what we are going to look at now is the activation functions and the backpropagation algorithm. And we're going to set that one up. We'll give you the basic details. And then after the break, we're going to look at how we can develop our own code for a neural network. So the activation functions, we want them to fulfill some properties, that we want them to be continuous. We would like to have nice derivatives. We want them to be monotonically increasing. We want them to be bounded and non-constant. So the typical function which is often used is the sigmoid or the hyperbolic tangent. And if you look at the plots of these functions here, what you would have then is something like what you see here. These are different functions. So this will be the sigmoid. The step function is not used. A sine function could be used, but it's actually not used. You have a tanh. And then there's a very popular set of functions which are called the rectified linear unit. And these are functions which are widely used in neural network training. And often since the values when z is less than 0, this is put to 0, what you would see now is that this can be tilted by a small parameter. So you would have something which goes up here is non-zero but small. That introduces an additional parameter. And then there are other functions as well which are being used here. If you now look at the multi-layer perceptron, one thing which is very important for us is that a neural network with only one layer, which is what we call a simple perceptron, that is best suited if you have a standard binary model with clear boundaries. So one of the things which is a very important aspect of neural networks is something which is called the universal approximation theorem, that states that a feed-forward network with a single hidden layer containing a finite number of neurons that can approximate continuous functions on a compact subset of real functions. And the theorem states that simple neural networks can represent a wide variety of interesting functions when given appropriate parameters. And then it's the multi-layer feed-forward architecture itself which gives neural network the potential of being universal approximators. So that's a very important theorem. And the basic algorithm for updating the weights is the backpropagation algorithm. And the backpropagation algorithm contains the gradient descent algorithm. So the backpropagation is you applying the chain rule to find the derivatives, which then give you the gradients, which then are used to train the parameters W, the weights, and the biases. So it's there are two stages here. One is the backpropagation algorithm, which is just an implementation of the chain rule, nothing but that. And then when you have the gradients, then you use a gradient descent method, like a stochastic gradient descent, to fine-tune the weights and the biases. And then you move back to the first hidden layer. You have updated the weights and the biases, and then you move forward again till the output layer. You have a new output. You compare that with the targets, and then you move back and forth till, like your cost functions, if we now are doing a regression problem, we want to fit a function, these are the targets, t, and y's are the outputs from the neural network. The output, this is what comes, y of I is what comes from the output layer. Now, in that figure which we draw, you see now that we have the inputs to a given hidden node in layer L. So this ZJL is the input to a given node in layer L. And that depends on the output from the previous layer. This is multiplied with the unknown weights, which need to be trained. And then we have a bias. And this would normally be written like a matrix times a vector plus a vector. And a typical activation function now is like the sigmoid function or the logistic function. And we would calculate this quantity. Now, the backpropagation algorithm is nothing but you using the chain rule. So we need some definitions now, because we want to calculate or minimize, we want to optimize this quantity here, starting at the output layer by calculating its derivative as function of the unknown parameters, the weights and the biases. That's essentially what we want to do here. So in order to do that, we need some intermediate steps. So in setting up the chain rule, we now need to calculate the derivative of these z's with respect to the weights. And you can simply show when you look at the mathematical function here, if I take this function here and I take the derivative of ZJL with respect to the weights, that gives me simply this A of L here, which you see here. And that's one of them. Then I need to take the derivative with respect to the previous input, and that simply becomes equal to the weight. So that's one intermediate step. And then we also need the derivative of the output as a function of the function z, and that can be given in terms of the function f, the activation function. So you can easily change, this equation here is generic, and that applies to any type of activation function. And then we need the derivative of the cost function. So in our case, what we have is a y of I, which is now replaced by the output from the last layer. So these are the weights in the output layer. And then when we take the derivative with respect to the weights, we have these expressions here. And then we need this one, this the last term here, which we have up here. So we can actually, using the chain rule, we can take this expression, and then we can, as you can see now, we can use the chain rule again, and we would replace this expression which you have here in terms of the derivative with respect to z, which we have up here. So that's this function. And then we need z with respect to w, and which we have up here. So that means that when we collect everything, we have that the derivative of the weights at the final layer for just a weight wjk in the final output layer is given by this function here. And then you can define, these are definitions which come here. So you can define a parameter delta, which now simply includes all these parameters. And then you can, if you proceed down, you can also show that, so what we have now is that the derivative of the weights at the output layer is given by this parameter multiplied with the input from the previous layer, L minus 1. You can also show that the biases, the derivative of the cost function with respect to the biases in the final layer are given by the same parameter. So if you bring everything together, what you have now is a set of equations. So you have the derivatives of the weights at the final layer, and these can be now used to calculate the gradients. And then I have this parameter, which is now given by the derivative of the cost function, and then the derivative of the cost function with respect to the outputs, times the derivative of the activation function. So these three equations are parts of the backpropagation algorithm. And then you need also to backpropagate to layers L plus 1. And then you're again using the chain rule. So now you have an update of this parameter delta J of layer L in terms of the inputs to layer L plus 1, and then the derivative of the cost function at the layer L plus 1 with respect to this function z. And with that, you have the derivatives in a given layer L plus 1, which then give you this update of this parameter in layer L. So what you have done now is simply to set up the mathematical quantities needed for the backpropagation algorithm. So when you're setting it up now, these equations which you see here, they form the basic elements of the backpropagation algorithm. So you would first set up the data set and the activation set ones in the first hidden layer. And then you would propagate everything through all the layers till you come to the last output layer. In the last output layer, you have the cost function which you have decided, and then you compute the output error. With the output error in the output layer, you can now go back, so you backpropagate this error for each layer till you reach the first hidden layer. And in each layer, you update the weights by simply using the gradient descent. And then this eta which you see here is the learning rate. So that becomes your parameter. It's a parameter which you need to fine tune. So this is the backpropagation algorithm. And that's the backbone in all neural network calculations, whether you do a convolutional one, a recurrent one, or just a plain feed-forward neural network. So the backpropagation algorithm gives us the gradients, which are these parameters here. It gives us the outputs from a given layer, which you see here, which are given by the activation function, which you have chosen. And then you have the parameter eta. And then everything is optimized with a gradient descent algorithm. So the backpropagation algorithm gives you the equations. The gradient descent algorithm gives you the recipe for updating the weights and the biases. And this is the basics of a training of a neural network. So what we are going to do now is to actually write a program which implements this. So what we're doing now is to set up the algorithm, and we are going to set up a multi-layer model for classification. So let me just go through, because now what we're going to do is to set up a what you will find in the slides here is the way you would do that for a classification problem with a binary case. But then you can also use this softmax function for a case with classification case with more classes. So the mathematics here is not so important. The basic thing now is when we want to develop a code. And what you will find here are the basic elements for writing your own neural network code. So there are the following basic steps. So you need to collect and pre-process the data. You need to define the model and architecture. You have to choose the cost function and optimizer, and then you have to train the model, and then you have to evaluate the model performance on test data, and then you have to adjust hyperparameters. So just to give you an example now. So we are going to look at the MNIST dataset, which actually contains 70,000 images. And you would have 28 times 28 pixels. So the dataset which is included in scikit-learn is a reduced dataset. And you will see that the quality of the images is not that good. But now you have 8 times 8 points. So we need to set up, so these are the features, the number of pixels. And then you have the number of inputs, which in this case would be 1797. So each row represents an input, in this case a handwritten digit, and each column represents a feature. In this case, this is a pixel. So the outputs are given then by a string of arrays, which are, and we label these as the targets. So this would be the number, the targets would be the numbers from 0 to 9. So there would be 10 possible outputs. So just to give you an example here, if you now have a very simplified case, this is your design matrix, which now predicts the body mass index and of persons with a given height, as you see here, in meters. And then you have the weight in kilograms. And then from that one, you can produce the body mass index. There's a formula for doing that. And this would be your output. So in this case, you would have a 2D matrix with 5 persons and 2 features, weight and height. Now, when we are now going to set up the data, scikit-learn has a data set, which are these digits, and that's a data set which I mentioned. And if we run this one, and we are setting up, I'm not going through all the details, but I wanted to show you the basics. You see that the numbers which we have now, so we have n inputs, we have 1797, and then we have pixel width and pixel height, so we have 64 pixels in total. So when I transform my matrix now, my feature matrix X has now 1797 images and 64 features. So this is the dimensionality of the problem which I'm dealing with. And then you see that when you look at the quality of this, okay, this looks like number 3. This is perhaps closer to 3. So the quality is a little bit so-and-so, because now we have only 8 pixels to label the figures. So if we were to go to the full data set, we would have 70,000, 28 times 28. So that would clearly become a very large matrix. And you can run that, still you can run that without problems. But if we were to run this during the lectures, it would never end. So we would not finish in time here. So the next thing we do now is that we split the data into train, test, and split. So I'm using the scikit-learn functionality to do that. And then we are just, I'm providing my own function for doing that, if you want to use that one. But you see what we have is a number of training images and the number of test images. So we have a training images, 1437, and then we want to apply this to the test cases. Okay, I'm going a little bit fast through things, but I want you to see the overarching things, because now we need to define the model and architecture. So we need to find out what kind of activation functions we want to use, how many weights we want to have, how many nodes, how many hidden layers we want to have. So we have to define the architectures, and these become parameters. So we need to define the number of input layers, hidden layers. So each input image has 64 pixels or features. If you use now 50 neurons, it means that since each neuron in the hidden layer is connected to the 64 inputs, we have 3,200 weights to train. And then if we add the bias, this means that we would have, if we were to, what do we need before starting the machine training? Okay, so what you need before you start the training is to set up your architecture. So if you go back now, if we now look at the, so you need to collect and pre-process the data. So in this case, scikit-learn can be used to collect and pre-process the data. Now you need to define the model and architecture. You need to figure out how many nodes you want to have and how many hidden layers. You need to know which kind of activation function you want to use. Then you have to choose a cost function and the way to optimize it. Then you train the model. And then when you train the model through the feed-forward network with the backpropagation algorithm, then you evaluate the model on the test data. And then you need to adjust hyperparameters. So these are the basic steps. So which you need to do before you start the training. So you need to figure out how to set up your network and how to define the parameters. So you need to split in test data, and now you need to set up the number of layers. We are just going to run with one layer. And the thing is that when you run machine learning algorithms, you have to decide on how many layers you want to have and how many nodes you want to have in each layer. And these become parameters which you can fine-tune to get the best possible fit of your model to the data. So I would suggest that we take a small break now and reconvene at, in this case it would be at 10 o'clock, right? Is that okay? If we just take a small break now, just stretch legs a little bit. And you guys, please feel free to unmute yourself and ask questions or write them in the chat.
Okay, thank you very much, Morten. Okay, let's have a little break till 10 o'clock. I'll see you around.
Let's do that. Eh?
Thank you.
And if people want to ask questions, just feel free to do that. så har det vært 5 ganger 1,5 da. Så det ble jo 7,5 timer da. Så totalt så har det tatt kanskje med forberedelse og alt ja, 15 timer. Ja, det har tatt litt mer.
The students are a bit shy this morning. Yeah.
Yeah, it's you know because now this is the 4th week, isn't it?
Yes. Yeah.
Yeah, so there is, I mean, there were 2 weeks of basic Python programming, and then you had this is the second week of the more, how to say, specialized topics, right?
Yes. Yeah.
So that clearly, yeah, that clearly takes it's 4 weeks and
Yeah. That would, and the usual conditions we would have like 2 weeks
yeah,
where yes, it will be more dense. Like in the morning, for example, there will be Python programming or kind of introduction to Linux sessions, and in the afternoon, more scientific subjects,
right,
kind
right,
of
right.
science-related, specialized subjects.
Yeah, the 2 weeks is 2 to 3 weeks is okay, but when you're getting into 4 weeks and it gets scattered out, I mean, it's the I'm impressed that we have that many people still here. What do you say, Ilya? Should we begin again?
Yes, yeah, it's 10 o'clock. Yeah, let's
Yeah.
continue.
Yeah, because I wanted to show how we can set up a neural network here. Now, the neural network, which we are going to train now on this data is a reduced data set. And that's simply because else I wouldn't be able to finish in time here with running the calculations. So we are going to so the architectures now, we're going to set up the inputs, which are 64 pixels per figure. And we have something like 1800 figures. We're going to use 80% for training. And now you see that the number of weights which you get, even for this very, very modest case, is something like 3200. And then we have an output layer, and that output layer now is a case which we want to tailor to 10 classes. So this is what we call a multi-class classification problem. And we are going to have 10 categories. These are the numbers from 0 to 9. And the activation function, so the output layer, you can actually choose different activation functions for the different layers. And typically in the hidden layers, you would normally use a sigmoid or tanh or one of these ReLU functions which we mentioned before the break. But then in the output layer, that's where you need to be a little bit more careful, and you have to tailor that one to the case you're looking at. So if your case is a regression case, you want to fit a continuous function, you don't use any activation function. You just spit out the value of that function given that specific input. Here we are going to use the softmax function, which is a probability. And this function here now so we are going to have 10 neurons because we have 10 outputs. And that means again that what we end up with then, with 50 nodes from the hidden layer, so we have 50, then there will be 500 weights to the output layers, which need to be trained. So the weights and the biases, then this is a very delicate thing actually. The weights and the biases, the way you initialize them plays also a very important role. And this was something which still is a big debate in the literature. So what you normally tend to do now is to initialize them with random but small values, and with random values given by the normal distribution. And the bias weights are either initialized to 0, but normally you give a small value to ensure that all the neurons have some output which can be back-propagated in the first training cycle. So in this simple example, which you will see below, what I've done now is to give the same bias to all the neurons in a hidden layer. You can change that. So if you now see what I'm doing, I'm simply building the neural network. So I'm saying now that the number of features and the number of inputs is now given by the training, the feature matrix. I specify the number of neurons to be 50, and I have 10 categories. And now I need to set up the weights and the biases. So what I do now is that I set up the weights to be given by random numbers. So I have the number of features in the model, and then I have the number of hidden neurons. And that's the dimensionality of my number of weights. So if you go back a little bit, in this specific case, we have, for the hidden layer, we have 64 inputs, and then 50 nodes in the hidden layer, so we have 3,200. And this is reflected in what we set up here, the number of features and the number of hidden neurons. And then the bias is now given by the number of hidden neurons, and plus just a constant, so I put them equal to 0. And I put the biases to be the same for all the hidden neurons or the hidden nodes. And then I have my output, and now I have 10 categories. So because I want to recognize these 10 numbers. And then the output layer needs also an output bias. And I just put that one to 0.01. So this is extremely simple. Normally when you run scikit-learn or TensorFlow, you will have much more refined ways of setting up these parameters. But this is to show you how easily you can calculate and set up your first neural network. So if you look at these Jupyter notebooks, you can now play around with it and actually develop your own code for setting up a neural network. And I think that's extremely useful, just to see what happens. And then we need to do the feed-forward pass. So what we do then, we compute the inputs from the outputs, the input to the hidden nodes based on the input layer. So we have one input layer and one hidden layer in this case. And then we have the activation function, which generates the output from the nodes in the hidden layer. And these are fed into the final layer, which is the output layer. And in the output layer, the output is now given by the softmax function. So basically what we need to do now are matrix vector multiplications. So the matrix which we have with the features, which now contains the number of inputs, these are all the images, the whole data set. And then we have 64 pixels, which are here, the features. This is now multiplied with the weights, and this is now what is being fed into this Z here. So that means that our Z of L as a vector is now given by the feature matrix times this matrix W, which contains the weights, and then plus the biases. So the output at the end is now given in terms of the number of inputs. So every input has obviously a set of pixels, and then I have the number of categories. And here's the setup of the feed-forward pass. I define the sigmoid function, which is now my activation function. I have the feed-forward piece, so you see now I produce the inputs to the hidden layers. So that's given by the matrix multiplication of x times the hidden weights plus the hidden bias. That's pretty straightforward. And then I produce the output, which is given by my sigmoid function, which I have defined here. And then I'm setting up the output, z of o. This is the input to the activation function, the softmax function. And then I have a matrix multiplication where I take this value and I multiply that with the output weights, add the output bias. And now I'm ready to compute the output, which is now given in terms of the softmax probabilities, which you see here. And that returns the probability. So this is my feed-forward pass. And then with the feed-forward pass, I can now make the prediction. And as you see here now, I'm making a prediction for all these images. And if I look at one specific image which I gave in, this image had a number 6, which was supposed to reproduce, but I reproduced number 8 here. So my model is not that good. So I predict number 8 by just one. So this is just a feed-forward pass. There is no training yet. Then I'm just going to skip some of these things here, because what we need now next is to implement the backpropagation algorithm. So we set up the inputs. We have the feed-forward part, which is the one we discussed above. So we produce the final probabilities, the outputs. And now what I'm going to do now is the backpropagation part. So I am computing now the error. So as a classification problem, I take my probabilities and subtract the output. And that defines the error. So this is my cost function. And then I produce the error in the hidden layer, where I now have I'm setting up what you see here now is my backpropagation algorithm. So that's going to produce the gradients. This input error here is now going to produce my output weights for the gradient and the output bias for the gradient. And then when I have that, I can set up the hidden weights for the gradient and the hidden bias for the gradient. So the hidden bias gradient and the gradient of the weights. And so this returns, this function which you see here now returns the gradients. And now I'm going to do the training. So in the training now, I'm going to have a learning rate. I'm going to have a hyperparameter lambda, which I just fixed like this. So this calculates the gradients, and it calls this backpropagation function. And then I set up the gradients and update them iteratively. So I would have this also this hyperparameter lambda times the output weights. And then I have the output weights now. So I'm updating weights and biases. So what I would have now is this learning rate eta, which is a parameter in my theory. And this is the output of the weights and the output of the bias, the hidden weights and the hidden bias. So I have an output of weights for the output layer. So I have only two layers, an output layer and a hidden layer, plus the input layer. So now I'm updating the weights and the biases using this backpropagation algorithm. And if you now look at the accuracy on the training data with just one backward pass, this is not impressive. So the accuracy on the training data is 0.14, and my prediction is actually, or the new accuracy on the training data after a backpropagation is 0.96. So the typical thing you would do now is to introduce hyperparameters. And these hyperparameters are parameters we would tune when we set up the network. So that means that we would have a a hyperparameter lambda, which goes from 10 to the minus 6 to, let's say, 1. And we would do the same with the learning rate. So the learning rate becomes also a parameter. And then we also need to set up things like the number of times we run through the stochastic gradient and so on. So these become parameters in the theory. We haven't had the time to discuss all these parameters properly. But the neural network class then, this is basically a repeat of what you saw previously. So I'm setting up the biases and weights. There's a feed-forward pass, and then we have the feed-forward output. And then there's a back propagation pass, where we're now updating the gradients. And then we have the training part, where we now run over the number of iterations which we want to set up. And then we want to evaluate the model and performance and test data. So what we do next is to calculate the accuracy. This is the kind of measure we are going to do now. And the accuracy is simply given by the number of correctly classified values divided by the number of data points which we have. So if there's a match, this is 1. If not, this is 0. So if you have if this accuracy is equal to 1, it means 100% perfect training. So the training now, I'm going to run now with a number of epochs and batch sizes which are used in the stochastic gradient descent. So I call my neural network function, which you saw above, and you see now that eta is a parameter, lambda is a parameter, the number of epochs and the number of batch sizes is used in the stochastic gradient descent. These are further parameters. The number of hidden neurons is also a set of parameters. And then we also have the categories, but they are defined by the problem which I'm looking at. And then I train my network, and then I make the prediction here. And in this case, the accuracy in the test score is not so bad. What I'm doing now is to adjust the hyperparameters, and I'm going to run with learning rates from 10 to the minus 5 to 1. And I'm going to take this hyperparameter lambda from 10 to the minus 5 to 10, as you see here. And then I'm going to train my network. And this is basically the output which you get. So you see now that if I have a learning rate which is very small, this means that it will make very small steps. The test accuracy is so and so. But then if you move down here, you will see that there are some optimal parameters. You will get to values like 95%. And then you can continue like this on your test data. But normally, instead of running through all this, you would use this Python package, which is called Seaborn, which allows you to display the data in a slightly nicer way using a heat map. So what I'm running now is just I'm running my network again with all the different hyperparameters. And then I'm calculating the predicted on the training data and the predicted on the test data. And then I calculate the train accuracy and the test accuracy. And the kind of plot you can make then is a plot of this type here, which you will see now coming up here. So this is my training accuracy. This is my learning rate. So if I have a learning rate of 10 to the minus 3 and a lambda value, which goes from 1 to 10 to the minus 3, you see that I have a accuracy here, which is basically 100%. And then also for a learning rate of 10 to the minus 2, I seem to have a pretty decent accuracy. So this is on my training. So Seaborn, this package is very useful to look at. But then I can do the same thing with the test accuracy. And you see now that with the test accuracy, I'm doing a little bit worse, but still for a learning rate of 10 to the minus 3, you have a accuracy of roughly 95%. Now what you saw here is me making a kind of grid search. So I set in a given set of parameters, and then I try to fine-tune my accuracy so that I can get the best possible accuracy. You could, if you wanted to, You could use a random search for these parameters. This is also done. So there are many ways of finding the best hyperparameters. But you see quickly that this becomes a boring exercise, because you would have to run these type of calculations for many different types of networks. You could have architectures with many hidden layers. You could have, it could even happen that the deeper you make it, the more complicated it gets, and it doesn't find a proper minimum. So you can implement everything which I did with scikit-learn, and that makes life much easier. So scikit-learn has this MLP, multi-layer perceptron classifier, and this makes life much, much easier than just writing your own program. I'm now setting up my deep neural network with scikit-learn. So I have still the same parameters, which we decided. So there's a function called MLP classifier. If you want to do a fit to data, you would have an MLP regressor. I need to define the number of hidden layers, the number of hidden neurons. I need to define the activation function, which is a new parameter. I have this hyperparameters lambda. I also have the learning rate. And I also have to set up the max iterations in stochastic gradient descent. So this uses by default a stochastic gradient descent. And then I use this scikit-learn functionality in this function fit. And then I'm just doing my setting up my final neural network here, where I'm setting in the data points for the number of or the learning rate values and the hyperparameters lambda. And then I use the score function, which now sets up my accuracy. So if I run that one with scikit-learn, this tends often to give a better result than my program. So my program was a pretty simple one. And scikit-learn has a more advanced way of finding the minima of the optimization function. So it's just going to run through all these variables. It takes some time. And this should be basically, it should almost be done now. It's soon done. Yeah, it's still running through some. So we are making a grid search over the best possible parameters. And you see also now that the score is getting better than what I had. In my case, the best score was 95%. So scikit-learn is now able to actually bring this up to 98%. And it's even getting into 99% here, as you can see. So it is an almost perfect score here. And that has to do with both the way the gradient descent is done and the way the cost function is being optimized with the gradient descent. So if we visualize the data, we can use the Seaborn package again. And you see now that they have a better, so it uses also an optimized learning rate. You will see that they have a better training result. So I have actually a chain of values for from eta from 10 to the minus 4 to 10 to the minus 2, which give a very good training, and even with 10 to the minus 1. So this clearly has a better way of doing the stochastic the gradient optimization. And then if you look now at the test accuracy, you see that you have a test accuracy of close to 100% for a learning rate of 10 to the minus 3. But what you see now, this is actually what you end up having to do when you deal with neural networks. You would need to train many of these hyperparameters, and then you will play back and forth with different types of activation functions. You will play around with different architectures and so on. But when you do scikit-learn, it's very easy to actually build it up. Now, the scikit-learn has, however, a limited functionality when it comes to neural network. It's very good when it comes to linear regression, logistic regression. It has all these functions with cross-validation and all that stuff. But the scikit-learn is somewhat limited when it comes to deep learning. And with deep learning, it's actually TensorFlow or PyTorch or similar libraries, which are the libraries which really give you the most flexibility, the best way to train. They have much more functionality. And there is an API which is called Keras on top of TensorFlow, which makes life pretty easy. So it was released by Google in 2015, And since then, this field has simply exploded. So it's the at the bottom, there is a C++ kernels that the TensorFlow is built upon. So that's because you end up dealing with huge matrices often, and you want to optimize the calculations. So you can easily install this if you're using Anaconda. I think nowadays Anaconda, when you install Anaconda, it already has TensorFlow. What you will see here is my application of using Keras. So I've simply plugged in Keras here, which is an API, which makes life a little bit easier. So we are going to look at the same data which we had, the MNIST data set. And what you would need now when you are going to run this case, so if I'm running this one, I'm importing the data. So this is the digits, the handwritten digits, which we're just importing here. And if I run this initial phase, you see now that I'm writing out some of the numbers, the handwritten numbers, which you also saw before. So we have 1800 inputs roughly and 64 features. Now with Keras, the way you would do this now is that you need to import different packages. So you would now to import the number of layers. So you have an input layer. You want to decide what kind of model. This is a sequential model, which means that it goes from layer to layer. You want to have a dense model. I want to build many different types of layers. You have to import the optimizers. There are many set of stochastic gradient optimizers. You want to decide whether you want to regularize. So if you want to use a ridge type hyperparameter or lasso type, you have to decide if you want to deal with classifications or not. So you now introduce something like the cost function, which is this cross entropy we discussed in logistic regression. And the thing which is nice is that it interfaces well with scikit-learn. So I have the train test split here from scikit-learn, which I can use again. So scikit-learn interfaces nicely with the TensorFlow and Keras. And that's useful because if you have written a lot of code now with TensorFlow, where you use that to structure your data, then you can reuse using that with scikit-learn, you can interface this function with TensorFlow and Keras. So here we have the standard approach, which we did before. We split into train and test. Now I'm defining the number of neurons in the first layer, so I have 100, and I take the number of neurons in the second layer, which is 50, and then I have 10 categories. And now I set up my space of hyperparameters. So these epochs and batch sizes are parameters used in the stochastic gradient descent. Here I now define that my first layer has now an activation function which is a sigmoid. It has an L2 regularizer, so it means that it takes this type of ridge type regularization. And then in the second layer I do the same. I have this L2, and then I use the sigmoid function. And then in my final layer I have my softmax function. This is my output. And then I decide that I want to use a stochastic gradient descent, and it has a learning rate which is eta, which is given by these set of parameters which I'm setting up here. And so this is my create the neural networks, and you can see here it's easy to add. So if you go into this one, you can easily add more hidden layers. So you can play around easily with different layers, different number of nodes. So you can change these parameters. You can add more layers and neurons and in each layers. Neurons in each layer. So it's a pretty how to say transparent way of setting up a neural network. So this is something we can now easily set up. And then when we now want to, this was a definition of the model which we have. So this is a function which I wrote, create neural network with Keras. And now I simply call this function. I have my loop over the hyperparameters, the learning rate, and the lambda parameters. I send in these inputs, and now I fit my equations, and then I evaluate the scores on the prediction which I make. So this is the fit to the model, and then the scores are now produced based on the test data and the test output and the test inputs. And then I'm just printing out everything. So if we now just run it, that this is going to be a little bit more. Oops, I have to trace back. What did I do here? So I think I tested this yesterday. Now sequential is not defined. That should be defined. I didn't run. I think I didn't run that one. Sorry for that. And now it should run. Yeah, now it's running. I just hadn't defined one of these. Oops. Let me see. I did something here. I actually wrote something wrong here. So this is the. I think I test now. This should be evaluate. I think. Let's see now. Now this is. Oh, I somehow. I've gotten some text in here which shouldn't be there. So I think this should be, yeah. I think that's the one here. Somehow I've been touching something. Yeah, there it comes. I actually, by some odd reason, I had my cursor must have changed something here, which I didn't see when I was trying to run it. So when using, there's a question in the chat here. When using a test data, what is the next step after pre-processing of data before training the model? So the let me see if I understand that. Yeah, so the one thing is to pre-process the data like we did now. But one thing you could do is that you could, in addition to the standard pre-processing where you would scale the data, what you could do is to try to reduce the dimensionality of the data. And one thing which many people use is something like a principal component analysis, where what you actually do now is to find those features which are the most important one by diagonalizing the correlation matrix. And then you would only keep those features which have a large eigenvalue in the correlation matrix. That would be a kind of pre-processing before you start using a neural network model. But I'm not sure what you mean when using an indigenous language here. So maybe we could discuss that one when we are done here. If you then look at the final plot here, you would get a similar accuracy as you had with the. You can see now when we use scikit-learn, you're going to get an accuracy of something like close to 98% on the test data. And this is still running, so it becomes always. So now it should be done. So let's now plot it. And then we're gonna pretty soon stop here. Now it's still running. It's still running. Yeah. So it's more time consuming compared to the calculation which I did with scikit-learn. Also because I have a network which is now deeper. I have two hidden layers. And what may happen with two hidden layers is that the model may not give better results. So sometimes you will find out that with just one hidden layer, you're going to get a better accuracy. So let's see if this is done now. I think it's done. Yes, it should be done now. So now we can plot it. And what you will see now when we plot it, if we now go through it again, so you will see now the following. So let me just bring this up again. You see now that the training accuracy is actually not as good as we had with scikit-learn, because with scikit-learn, with just one hidden layer, we had something like ones here, almost all the way. And it had a better performance for even 10 to the minus 2. So this may be an indication that one hidden layer is perhaps enough in training this model here. And if we then go to the test accuracy, you remember that with just one hidden layer and scikit-learn, we had a 99% accuracy. And now the best one we get is 98%. So you see now the different parameters which you need to train and play around with. And you would then find the optimal network which gives the best possible result for that specific data set which you have. Now, there are more examples here, and you can play around with them as you want. One is the breast cancer data. Again, we discussed that one on Tuesday in connection with the neural networks. But you see now, one of the tools, one of the things you need to think of is to fine-tune the different parameters. That's a very important aspect. There are actually tools which allow you to do that. One is called Oscar. You can use a grid search with cross-validation to find the right hyperparameters. And people have also been using a random search. And for many problems, you can start with one or just two hidden layers, and that will work fine. And for the MNIST data, you saw that just one hidden layer with a few hundred neurons does a fantastic job. The question is also which kind of activation function you want to use. So you would have to decide on the activation functions. You would have to decide on the kind of gradient method you want to use. So the logistic function is a function which actually almost killed the field till 2010. And there's this paper by Glorieux and Benjo, where they actually analyze the problems you had in training neural network with a sigmoid function. And that unleashed a lot of research on finding alternative activation functions. So the sigmoid function was a function which, since it's very flat for high values of the input, it could often lead to vanishing gradients. So when you took the derivative, it gave you zero derivatives. And that caused problems in the training, because in the training of a neural network, in the backpropagation algorithm, you don't want the gradients to disappear. Normally, when you want to optimize and find the minimum, you want the gradient to disappear. But you don't want that with a backpropagation algorithm. So there are many things here. So there are functions like the ReLU function, there are modifications, exponential linear unit function. So there's a lot of room for improvements here. So you see the active fields of research deal with improving the activation functions, finding better ones, but also in the gradient optimization of the problem. So if you can cook up better ways to optimize these multidimensional surfaces, then you will become very popular. That's my guess. Let me conclude now a little bit on, there are many other things here which are used to train the networks. And if you look at the neural networks, they have some pros and cons, obviously. One of the limitations is that you need labeled data. And they are very data intensive. Remember again that we have a full matrix or matrix vector multiplication, so we deal with the full dimensionality of the problem. So that's one problem. It deals only with homogeneous data. If you have heterogeneous data, then I would recommend gradient boosted trees or random forests. And many problems in science are not about prediction. So you may make a good prediction but still have a wrong model. So to figure out which is the best model is also a very active area of research. And what you end up with at the end is to try out all these different parameters in order to, if you're interested in fitting a function, you will end up training various models. And the essential thing which comes back then is this bias variance trade-off, which is a kind of a central aspect of how you gauge whether this is a good or bad model. Now, CNNs and RNNs, I see my time I'm running out of time here, but convolutional neural networks are extremely popular, and they are also very popular because they reduce the dimensionality of the problem. There's a lot of more material here, so feel free to use that one, or just send me an email if you want to about more details. The aim today was to give you a kind of bird's view on how you can write your own neural network, and then how you can use TensorFlow or scikit-learn to set up a efficient way of calculating or computing with a neural network. So this is going to end my lectures. Feel free to use the material. There's more material here, also on decision trees, which we didn't have time to look at. So I'm going to stop here now. And thanks for being with me all the time. Feel free to use the material as you want. And hopefully, for those of you who have not studied machine learning, it can serve as an entry point. And you guys use the codes as you want. And everything here, you see, you have Jupyter notebooks, everything you need. Okay, guys.
Okay.
Yeah.
Thank you, Morten.
Yeah.
I think, if you would comment on that question from the Mercy, I think what the person meant is what to do not with the test data, but with the text data, especially if it's a text data from indigenous language. It's meant probably African language, for example, isiZulu or Xhosa, and so on and so forth.
I'm sorry for that, because I read test data. I see that it says text data, but then I just read the test data. So, sorry for that. My mind was not set to read correctly your test. So probably I have some faulty machine learning inside here. So that's a good point. So if you think of machine learning on text, there's actually quite some progress there. So one way you would use machine learning would be using recurrent neural networks. So recurrent neural networks have been used to train in language recognition, and that's one of the perhaps central algorithms in, let's say, in Google Translate. But then what you have is also text. Also, you can use machine learning on text. That's a field by itself, and I'm not an expert on that one, but there are actually several good textbooks on applying machine learning on text analysis. I have a colleague who is actually dealing with the analysis of translation of laws in the European Union, because they're often written in the main languages, and then they're being translated to Hungarian, to Croatians, or things like that. And then they use machine learning to see that the translations comply with the basic laws, the way they're written in, say, English, German, and French, which are the main, and Spanish, which are more the main languages. So the machine learning on text data is actually a very active research field, and I'm not an expert on that one, but the only thing I've been using is some simple recurring neural networks on simple text. There are some more questions here, actually, on physics, applications of neural networks in physics. So there's a whole field now in quantum mechanics, where you try to solve quantum mechanical problems using neural networks. And I can show you a paper here. I can just punch it in here if you're interested. And it should be that paper here. So that's a variational. If you look at this paper, this is a variational Monte Carlo calculation. And in variational Monte Carlo, what you do is to solve, you actually perform a Monte Carlo integral, and you take the complicated correlation part of the wave function and you replace that one with a neural network. So you let the network then train so that you try to extract the complicated many particle correlations with a neural network. So that's a very hot field of research. You have this paper by Giuseppe Carleo. Let me just show you that one as well. I'm going to put this one in the chat here so you guys can, let me just put the link in the chat. So that's one of the papers. That's a very big application. You have the paper by Carleo where you use something which is called Boltzmann machines. Let's see, Carleo and Troyer. So this was a science paper in 2017. And Giuseppe Carleo has actually developed many new methods for solving many-body problems. So this is it's a very nice read. Actually, if you're interested, I have lecture notes on this, where you can even look up my programs if you want to, and just solve a many-body problem using so-called Boltzmann machines. So I can give you the link to that one as well if you want to. So let me just give you that link. You can then, so let me just give you that one. So what, notebook 2 here. So there's a Jupyter notebook here. And let me just send you that link. So if you take the Jupyter notebook here, you can reproduce the calculations by Carleo and company, but on another system, which is a quantum mechanical 2-electron system. And that notebook introduces something which is called Boltzmann machines. Then if you go into particle physics, you have tons or nuclear physics where you want to classify the results of experiments, whether this is a beta decay with 1 electron or 2 electrons and so on. Then you would just take your images which you get from the detector, and you would then simply use that one to classify different types of events. So classification of events in particle physics, nuclear physics, or other types of reactions are widely studied with machine learning methods, because you have so much data that's almost impossible to go through all the data. So that would be another application. There's another cool application, which is the classification of pulsars in astrophysics. So the number of applications are just many applications. I see that there are more questions here. So that was one applications in physics. So I hope that gave you something. There's a question from David. He has raised his hand here.
Yes, Morten, I just thought that it's important for us to say a huge thanks to you for the fantastic notes and things that you've put out there, the Jupyter notebooks, and also all the references, and also your very detailed way of taking us through writing the code yourself, then using scikit-learn, then using tensors, etc., so that you can actually see what's going on without just diving in and using the packages blindly, which I think is a great way of teaching. Thank you very much.
Thanks, David. That really warms. I mean, that was my hope, because I knew that you guys had gone through all this Python programming, so I tried in a way to interface this with what you had seen before, so that you could reuse the 2 first weeks. And the other hope was more to demystify many of the parameters, because people tend to use these things as black boxes. And most of you are physicists or are going to be computational scientists, and you are the guys who are going to develop the next generation of black boxes. And then it's very useful to actually understand what's going on behind the curtains. I think that's important. Thanks, guys.
Okay, Morten.
Thanks for being so patient.
Thank you very much for the very nice talk and for the very nice lecture series. Okay, I think now you have a, again, difficult task of choosing the best question.
Now, there was a, let me see now. I'm just scrolling back here. All the questions are excellent. So I'm just going to almost toss the coin here, and the maybe I think the question which Tajuddin asked about the computational efficiency of the activation functions is a very important question. So that could be one. I would give a book voucher to everybody. But maybe we say I'm tossing the coin now. I mean, let's say Tajuddin here with the activation function. That's a very important question, because these activation functions are chosen so that you have normally analytical derivatives, and they also have to be efficient to deal with, and you want to have gradients which are not vanishing. So it's a very delicate aspect in machine learning.
Okay, very good. Tajuddin, could you please send your email into the chat so that I can pass down the information to Francesco? Okay, I assume that Tajuddin will do it just now. And yeah, thank you very much, Morten. I think it was very interesting set of lectures.
Thanks.
Yeah, I think what is even more impressive is your GitHub repository with kind of more extended courses on machine learning, including the link which you just shown to us. And I think everyone who wants to know more are more than welcome just to go there and just start to going through the more tutorials.
Please feel free to use this material as you want. I mean, we are public employees, and one of our jobs is actually to spread knowledge. Use it as you want.
Okay, thank you very much.
Okay, guys.
Thank you very much, Morten.
A pleasure to meet you.
I think we can. Yeah, it was also a pleasure to meet you, and we can wrap up this session. But I'm sure that in the moment when we can do the summer schools offline, we'll be more than happy to see you here in South Africa.
I would love to be there. I've been there once, and I would love to come back again. Really. Thanks, guys.
We would also be very happy to see you around. Thank you.
Care.
Thank you very much. Bye-bye.
Bye.